Welcome, everyone. My name is Ricardo Camacho. I'm the Director of Compliance in Software Safety and Security at Parasoft. And thank you for joining us today for this presentation on ensuring artificial intelligence and machine learning safety in embedded systems. Now, I've sat through my fair share of AI presentations. Many of them kind of dive into model architectures and also the underlying mathematics. And while those technical details matter today, I want to take a different approach. We're going to zoom out and focus on the bigger picture, how AI and machine learning are being applied right now in embedded safety critical systems, because here's what I've observed. Adoption varies widely across industries. Some are racing ahead, while others kind of hesitate due to actual very valid concerns about safety and reliability. So my goal is to address those concerns head on, share practical insights, and hopefully give you the confidence to move forward with AI if you haven't already. Anyways, let's get started. First, I'll begin by discussing why AI and ML are increasingly being used in embedded systems. Then I'll cover the challenges related to ensuring safety, maintaining determinism, and meeting compliance requirements. I'll then walk through some of the techniques and advancements that can be applied to help address these challenges, particularly how to achieve safety compliance when you integrate artificial intelligence. Now, this includes traditional software test verification methods as well as additional approaches specifically needed to verify and validate AI and ML components. I'll conclude with a brief outlook on the future of AI in embedded systems, and then we'll follow it up with Q&A. Now, we all know AI is revolutionizing embedded systems. It's making devices smarter, more responsive, and frankly, more indispensable to users. Think about it. Your smartwatch doesn't just count steps anymore. With AI, it can track your heart rate, run an EKG, even recognize whether you're swimming, cycling, or sleeping. I use mine religiously, and it's just one example of how AI is reshaping industries from healthcare to automotive to energy. But here's the critical distinction. The AI in your Fitbit or smart thermostat isn't the same as the massive models powered by ChatGPT. Cloud-based AIs like ChatGPT run on sprawling server farms with near unlimited resources. Embedded AI, however, it's the opposite. You got to squeeze intelligence into devices with, small budgets, low memory. You can't use a whole lot of power, and they may be even limited in processing. So we're talking about on-device AI or TinyML or Edge AI, all terms for models that must deliver smarts within tight constraints. Let me put this also in perspective. Now, McKinsey predicts 70% of embedded systems will integrate AI by 2030. It's already here in your smartphone camera, your car's safety system, even autonomous taxis. My son in Arizona uses Waymo self-driving cars daily, and and I'm still kind of working up to get the courage. Anyways, the takeaway: embedded AI isn't the future; it's now. And on the next slide, we'll dig into how to make it work when every byte and milliwatt actually counts. Okay, let's go through some of the key challenges of adopting and integrating AI and ML into your embedded systems. One of the first concerns is safety. Safety critical systems demand predictable behavior every single time. Imagine an AI controlled braking system in a car that hesitates or reacts inconsistently. A 100 millisecond delay, well, that could be fatal. And here's the problem: AI is inherently non deterministic. So, same input, different possible outputs. That black box nature clashes head on with standards like ISO 26262 in automotive or DO 178C in aerospace, where maybe is not an option. Also, hackers could exploit the AI by feeding it adversarial inputs that could compromise the integrity of the embedded system. For example, it can be as simple as adding a sticker to a stop sign to cause it to misinterpret it, that it's not a stop sign, or spoof the GPS to mislead the vehicle's navigation system, or spoof the LiDAR or camera or radar or sensors and have it misinterpret objects that they may see. Anyways, I'll talk about how to protect against these challenges later in this presentation. Now, another major challenge for AI and embedded systems is size constraints. AI/ML models require significant computational resources, which can lead to performance bottlenecks and increased power consumption. This makes power and memory usage critical factors. For example, embedded devices like smartwatches and rings have limited memory and battery capacity, so the AI model size and power consumption must be kept to a minimum. Now, there are other challenges, but I want to touch on hardware. It's a good place to start because there are specialized chips designed to run AI efficiently on embedded systems. So AI execution involves massive amounts of parallel processing, matrix multiplication, and multi-dimensional array computations. So general purpose CPUs struggle with this because they're not optimized for such tasks. That's where GPUs come in. They have thousands of cores designed specifically for parallel computation, which makes them well suited for AI workloads. However, in the embedded world, GPUs aren't always the best fit. They're power hungry, often expensive, and typically designed for use in cloud environments, not on the embedded device itself. So to address this, we have neural processing units, or NPUs, specialized chips designed specifically for embedded systems. NPUs excel at the kind of multidimensional array processing required for AI. Their efficiency leads to lower power consumption, better performance, and cost savings, making them ideal for applications like image recognition and other AI-related tasks in embedded devices. For example, Qualcomm builds NPUs used in smartphones that have achieved up to 35% reduction in power consumptions. Now, similarly, there are Edge Tensor Processing Units, or Edge TPUs, developed by TSMC for companies like Google, NVIDIA, AMD, and others. These are purpose-built for embedded AI and are commonly found in smart cameras, drones, and similar devices. Now, on this slide, I've included a table to help illustrate the different types of AI hardware along with some of their pros and cons. GPUs are fantastic for AI and are often used in large server farms, but again, their size, energy demands, and costs make them unsuitable for embedded applications. You also have cloud TPUs, where they were developed to address some of these drawbacks with GPUs. They're more power efficient and cost effective for remote AI workloads. Then you have edge TPUs. They take it a step further. They're optimized for embedded systems, offering lower power consumption and better efficiency. NPUs are designed solely for embedded. They're not used in the cloud. They're built for high energy efficiency, strong performance, and low cost. So the hardware is here and it's rapidly evolving. Smaller, more efficient AI chips are actively under development, and they're continuing to accelerate what's possible with AI and embedded systems. Now, these embedded chips are heavily used to exercise environmental data, sensor data like accelerometer data, LiDAR data, or simplified object identification data. So the data size is not as large as a LLM like ChatGPT, but size is still a concern. So let's start addressing this concern with learning about compressing AI models. Now, I'm going to oversimplify things a little bit here, but on the right, you can see a diagram of a simple neural network. What you're looking at are nodes or neurons, and each one has its own weight and threshold. These neurons pass information to one another. The nodes are organized into layers. You can think of each vertical alignment of neurons as a layer. There are usually multiple layers depending on the complexity of the task and the type of input data. Now, the layer on the far left is the input layer where the data enters. The one on the far right is the output layer where the results come out. Everything in between is part of what we call the hidden layers, and this is where the model does its learning. Now, neural network models, especially deep ones, can consume a lot of memory and processing power, and to deal with that, one common technique is called pruning. Pruning is a way to compress the model after it's been trained. You essentially remove the nodes and connectors that are rarely activated, or you can remove layers that contribute very little to the actual final output. So this helps reduce both the size and the computational cost of the model. Of course, you do lose a bit of accuracy when you prune, but the goal is to maintain about 95% of the model's original accuracy while eliminating up to 40% of the connections. And after pruning, you can still fine-tune or retrain the model to recover any lost performance. An example of this in action is the Mars rover, which used a pruned neural network to improve processing efficiency. So the result, it ran about 30% faster than when using the original unpruned model. So this was a huge savings. Now, you can actually take pruning a step further if you want to reduce the model size, lower memory usage, improve speed, and decrease power consumption all at once. You can use a technique called quantization. Quantization works by taking a fully trained or even pruned model that uses 32-bit floating point weights and activations and converting them into a version that uses lower precision values like 16-bit, 8-bit, or actually even 4-bit integers. Yes, there can be a slight drop in accuracy again, but often you can retain or fine-tune the model at the lower precision to recover much of that lost accuracy. Take, for example, Fitbit. They moved from a 32-bit solution to an 8-bit and were actually able to reduce power consumption by 30%. That's what enabled continuous heart rate tracking on their devices for 5 to 7 days without needing a recharge. And they actually very proud of this. They branded that capability as Pure Pulse technology. And here's a quick analogy I like to use. Quantization is like compressing a high resolution photo. You're keeping the core image intact, but you save a lot of space. And for embedded systems where every bit of memory and power matters, that's a game changer. All right, so let's talk about risk, because if you're working with AI in things like self-driving cars or medical devices or robots, risk isn't just part of the job, it is the job, right? Even old school systems like airplane autopilots fail sometimes. And AI also adds new risks, but also it does provide game-changing capabilities. So here's the thing, we're not chasing zero risk, that's a fantasy. We're chasing tolerable risk, like an autonomous car shouldn't just be as safe as a human driver, it's got to be actually safer. Now, this is where engineers earn their pay. Risk isn't something you just cross your fingers and hope for the best. You actively actually manage it. And how do you do that? Well, you throw everything at it. Formal verification to prove your AI won't go rogue, millions of virtual miles in simulation. You include backup systems, so redundancy, and real-time monitoring, so the AI screams for help before it actually screws up. Regulators, users, everybody needs to know what can this AI actually handle and where does it actually tap out. So when is rolling the dice on AI okay? Well, there are three big reasons. Net safety gain, like a self-driving car that crashes less than humans. There's no better option. Think about AI being able to spot tumors where humans or doctors are likely to miss it. Also, AI is controlled and mitigated. You're following rules and regulations and guidelines like ISO 26262 and other standards that actually keep the AI risk on a leash. So let's talk a little bit about some of these standards. Just last December, ISO dropped a new standard, ISO 8800-2024. What's it about? Well, it's basically a playbook for making AI in cars safer. It takes the safety lifecycle from ISO 26262, the gold standard for automotive functional safety, and tailors it specifically for AI systems. For example, how do you derive safety requirements for AI? What architectural safeguards do you need? And crucially, how do you verify and validate that the AI behaves as expected? Now, so that new standard exists, and you can also pair it with IEC TR 5469, a complementary guideline. It's all about integrating AI into safety critical systems without actually blowing things up. It gives you the how-to for keeping AI in check when lives are on the line, like in self-driving cars or medical devices. And here's the interesting part. Compliance is a beast, as I'm sure you're all aware. You've got ISO 26262 for cars with those ASIL levels, A through D. And over in the medical industry, there's IEC 62304, and aerospace has DO 178C. So each of these standards force you to ask, for example, how safety critical is this component? Or what's the worst case risk? And regulators like the FDA are piling on with AI-specific rules for healthcare. So the bottom line is certification isn't just about building smart AI. It's about proving that it's safe. That means crazy amount of documentation, traceability, show me exactly how this neural network was trained, and what are the guardrails in place. Because yes, neural networks, they learn, but sometimes they learn the wrong thing. So you need hard-coded rules as a safety net. Like a parent actually teaching a kid to ride a bike, but keeping your hand on the seat so that they don't fall off. Now, standards like ISO 8800 and TR 5469, they're the guardrails for the industry's AI race. The problem is that tech moves faster than the rules, so you're going to have to buckle up. A little automotive humor there. All right, let's talk about those guardrails. Now, guardrails, they play a critical role in making sure AI systems behave the way we expect, reliably, safe, and ethically. So what do we mean by guardrails? Now, these are built-in mechanisms or constraints that keep an AI system operating within safe and acceptable boundaries. So you have to remember, AI doesn't operate on its own. It's actually part of a large hybrid software architecture. And that surrounding system that the AI runs in, can monitor and measure what the AI is doing and step in if needed or if it's necessary. Now, let's take a self-driving car as an example. The AI might predict that the best speed for a smooth ride is 85 miles per hour, but guardrails can enforce the rule that the car must stay within the posted speed limit. It can also make sure that the car doesn't accelerate towards a stationary object and slam on the brakes at the last second or enter some restricted zone like a school area. So these guardrails can also be fail-safes. So if the AI model fails or starts acting unpredictably, the system can safely pull over or even hand control back to the human driver. Now, these mechanisms are super important, especially because AI models, particularly large ones, can hallucinate or behave in ways that we didn't see during training of those models. And the good news is that we can test these guardrails. We can simulate edge cases, log what happens, document the results, and verify that everything works as expected. That's huge when it comes to compliance and safety certification. Now, of course, putting guardrails in place is just one piece of the puzzle. If we're going to certify AI for use in safety critical systems like in aviation, automotive, or medical devices, we also need to show that we've actively worked to prevent unintended failures. So rule-based guardrails help us get there, but they're only part of the larger compliance strategy. There's more strategies to come. So let's move to the next one. So one of the biggest challenges with using AI in embedded safety critical systems like what you find in autonomous vehicles is making sure that the system behaves in a predictable, consistent way. In the automotive world, safety standards like ISO 26262 are very clear. The system has to act the same way every time, no matter what. So if you've got a whole fleet of autonomous vehicles like Waymo cars, they all need to respond the same way in the same situation. You can't have each one of those vehicles developing its own personality. So to make that happen, developers use a process called freezing or locking the AI model. What that really means is that once the model has been trained, tested, and validated to meet all of the necessary safety, performance, and compliance requirements, it's locked down. There's no more tweaks, no more training, unless you go through a formal change control process. So that's crucial for safety critical environments. Freezing the model ensures that the same input always leads to the same output, even in those tricky edge cases. This not only prevents unexpected behavior after validation, but it also makes it possible for regulators and safety engineers to confidently certify the software. They know the exact version that was validated, that is going to go out into production, that the model maintains its safety integrity level or SIL without any surprises popping up down the line. Now, if we want to get technical, freezing a model means its weights, architecture, and hyperparameters are locked in. Nothing changes after validation. And to make it more relatable, think of it like a McDonald's cheeseburger, where, whether you're in Tokyo or Texas, that cheeseburger is going to taste exactly the same. That's the same idea here. Frozen AI models should behave the same way every time in every vehicle, no matter what the environment is. Now, this isn't just theory either. Companies like Tesla follow this approach with their autopilot system. They lock the model to make sure each vehicle behaves exactly as it did during testing. That predictability, again, is crucial. Without it, regulators simply wouldn't allow these cars on public roads. And platforms like NVIDIA's Drive, which is ASIL-D certified, are being used by several automotive OEMs for exactly this reason, to support safe, deterministic AI behavior in production vehicles. All right, let's get into testing. Because at the end of the day, testing is really the cornerstone of software verification, validation, and ultimately certification. And even though we're dealing with AI now, the traditional techniques, things like static analysis, unit testing, code coverage, and requirements traceability, are still absolutely critical. These aren't outdated or going away. In fact, they're evolving to meet the demands of today's more complex systems, especially with AI in the mix. Now, take static analysis, for example. We can now use it on Python code that's used to develop AI models, like those built with PyTorch or TensorFlow. It helps catch common issues early on, like uninitialized variables, insecure coding practices, or even broader code quality problems. Now, that said, static analysis is only one piece of the puzzle. You still need dynamic analysis, things like unit testing and integration testing. Now, why? Because you want to make sure the entire data pipeline, everything from how the data is pre-processed to how it flows into the AI model and how output is handled, is solid. That means checking, is the output data valid and within expected ranges? Is the pre-processing logic working correctly before the data hits the model? And once the model gives you an output, is that output valid, interpretable, and tie it back to your expected behavior? Now, even the idea of code coverage is being adapted for AI. Instead of just checking which lines of code were executed, tools can now look at something called neuron coverage. That shows you which parts of the neuron network actually got exercised during testing. It's really helpful for spotting neurons that are never activated. Those might be dead weight that you can optimize or prune, which is important for both performance and safety. And of course, none of this really matters unless it's traceable. Just like in traditional software development, you need to be able to show that the right tests were run, what was the results, and how they actually link back to the system's requirements. That traceability and documentation is what compliance demands on, and it's how you prove that your system, including the AI parts, is safe and ready for deployment. So let's talk about this black box. When we talk about safety and compliance, one of the big concerns a lot of folks have with the AI is that it is seen as a black box. It makes decisions, but you don't really know how, and that's a problem, especially in safety critical systems like self-driving cars. How do you know what it's going to do, that it's going to make the right decision, when it actually really matters? Like, will it brake in time if a person suddenly walks in front of it? So that's where explainable AI, or you may see the term or letters XAI, that's where it comes in. It's all about making the AI's decision more transparent. So some models actually already come built in with this explainability capabilities in mind. But even if they're not, there are tools like SHAP and Lime and even PFI where they can be added on to give you insights into why the model made a particular choice. You may have seen something similar to explainable AI in tools like DeepSeek and ChatGPT when you turn on reasoning. When you turn on that reasoning and you ask it questions, you can see the logic that it goes through. It actually starts to show you how it's arriving at its answer. So that's very similar, but in much more depth and much more granularity. So in the self-driving car example, you could see that the AI recognized a person, understood the danger, and chose to brake. So that kind of transparency builds trust, which is huge when you're trying to certify or validate these systems. XAI also helps a lot with debugging. If the model makes a bad call, like misclassifying a stop sign, you can use these explainability tools to figure out what went wrong and where. Was it the lighting, the angle, something in the data? So you can trace it back and actually fix it. Now, during development, especially in automotive, most of these testing happens in simulation. You can throw all kinds of scenarios at the model. Pedestrian crossings, edge cases, weird weather conditions, and then use XAI to see not just what the model did, but why it did it. So in the end, explainability helps turn that AI system from a black box into a clear box, one that you can verify and trust to behave consistently in real world situations. Now, when we talk about safety and certification in AI systems, resilience is absolutely critical. I mentioned earlier how freezing models gives us the predictability, but in safety critical applications, that's actually still not enough. We actually need real fail safes. So here's how the industry is solving this, and they're doing it through redundancy. So just like commercial aircrafts have backup systems, we run multiple identical AI models in parallel. For example, take Tesla's approach. They don't rely on just one AI instance processing sensor data. They run duplicates simultaneously. If one fails due to a sensor error or glitch, the other keeps functioning seamlessly. Think of it like having backup drivers always ready to take the wheel. And we take this even further for maximum reliability. Many organizations implement a voting system among these independent frozen models. Each processes the input data separately, then a voting mechanism makes the final decision based on majority consensus. This triple redundancy approach gives us robustness against individual model failures, consistency in decision making, and compliance with strict standards like ISO 26262. So anyways, the key takeaway here is that AI is already being successfully implemented and certified in safety critical embedded systems today. These aren't theoretical concepts, they're proven engineering solutions that remove the guesswork and risk from AI development. Okay, now before we wrap up, let's take a quick look at where AI is headed because this technology is evolving fast. First, embedded AI is going mainstream. Embedded AI is moving away from cloud-dependent models to smarter self-contained devices with onboard AI. That means faster responses, better privacy, and no reliance on connectivity, which is really, really important. Now, on the hardware side, breakthroughs are continuing to come. You can now think about a 2 nanometer AI chip, smaller, more powerful, and ultra efficient. This is a game changer for edge devices where every milliwatt matters, and TSMC is actually kind of leading that charge. Privacy is also getting a major upgrade. Federated learning will let AI train on your data without actually ever sharing it. So your devices are getting smarter, but your personal information is also staying local. We're also making AI more transparent and secure. Explainable AI will demystify decisions so we can trust and debug AI models a lot easier. On security, AI will play defense against next generation cyber threats, even when it comes to quantum computing attacks. And here's a trend I love. AI is becoming a co-pilot for engineers. Tools like Parasoft already use AI to auto-fix bugs flagged by static analysis. Not only can they organize violations or issues found, but they can also automatically generate code or suggest code for you to fix coding violations. So again, the bottom line is AI isn't just coming to embedded, it's redefining what's possible. And this is actually just the start, I would say. To wrap it up, AI and machine learning are no longer futuristic concepts. They're essential to embedded systems today. From automotive to healthcare, they're unlocking new capabilities. But let's be clear, they're also bringing real challenges in safety, security, and compliance. Now, the good news is we've got solutions. Through pruning, quantization, we're making models leaner and faster. There's also specialized hardware, which is pushing performance boundaries. There's explainable AI, which is building trust, and while also redundancy ensures fail-safe operations. And by combining AI with rule-based guardrails, we're achieving what once seemed impossible. which is the deterministic, certifiable AI for safety critical applications. Now, looking ahead, AI's role in embedded systems will only grow, but it'll grow responsibly. The key is balancing innovation with reliability and progress with compliance. Okay, so anyways, thank you all for your time today. My goal again was to demystify how AI can be adopted safely and effectively in embedded environments. That concludes the presentation, so let's open it up for Q&A.